coming from Yingming Hua. I'm presenting it here. What is atomic resolution? I just spoke about that. What are the conditions to achieve it on mica, HOPG, and calcite? So HOPG, for instance, again, you can have a 3D image on a larger surface. You can single steps there. If you go then for the mica, you can see here atomic single oxygen atoms on the surface. On the from the mica layers, contact mode with an AFM. Here you use an STM scanning tunneling microscope to use the tips, to use metallic tips to measure on a metallic or conductive surface, where you can achieve atomic resolution on HOPG. Or like here in peak force tapping mode, you can also see atoms on calcite. Again, what is important is it has to be an organized structure, otherwise you will not see that with an AFM at room temperature or in air or in liquid actually as well. So what do we have? Again, low noise XY scanner. You have to have a low noise in Z. You have to have a sharp tip and a small and soft cantilever. Again, coming to that later. So now, caught up, I think, with what I said just before is now you have to control the drift of your system to stabilize the system to reduce the drift. Otherwise, again, since you're measuring in the nanometer range, and if your drift is too strong, you will always, your system will drift out of, your items will drift out of your image. So you have to, one possibility is to scan fast to reduce this drift effect. The other thing then is the contamination control. So you have to have a fresh sample and a clean solution if you work in liquid. I'm showing later some images on that. And the most important thing actually, what I think is, again, is practice, patience, and confidence. Meaning, so if it's not working the first time, as it happened to me this morning when I tried to set something up, you need to try different approaches. You need to keep cool, and you need to think about what might be the causes of error. And if you can eliminate them, then you can get to a nice atomic resolution. So for instance, how to achieve atomic resolution on mica in contact mode, which is a nice thing. So you can use, for instance, the multi-mode with the E-scanner. Let me just pull this slightly to this. No, it's okay. So you can use the multi-mode with the E-scanner, meaning the scan size goes from several nanometers up to 10 microns about. You can also use for the multi-mode the A-type scanner, which is then only in scan size about 0.7 microns in X, Y, and Z, but this is giving you a nice atomic resolution in contact mode, in air, or in fluids on mica pretty easily, because it's the scanner we offer with the lowest noise actually. So, however, but you can achieve also with the E-scanner atomic resolution. So as an example for a good probe for that is the SNLC probe, which is the standard silicon nitride lever, which is used for tapping in fluid or contact in fluid. But you can use that again for contact in air as well. Scan size should be about 10 nanometers, and you see here the scan rate. Usually you scan even with an E-scanner in contact mode with 2, maybe 4 hertz. Usually more around 1 hertz. Your P and I gain should be pretty low, so at 0.2. Your scan angle should be 90 degrees, because the best channel, again, to measure the atoms, to see the atoms, is the friction channel. So therefore, you have to scan 90 degrees. The deflection set point should be at about 0.2 volts. And I'm coming to the rounding later a bit. So this means to minimize artifacts from the scanning, because you're scanning very, very fast. The resolution should be, in this case, 512 times 512 data points. And again, the channel should be friction. So what you could usually do for the setup is use either a tripod or the air table, and you have to use this foam enclosure actually, which you see on the right-hand side photo, which seals off the acoustic noise. This would be for the multi-mode, so ideally again a tripod with bungees, or use our standard air table. Or if you work with an icon or fast-scan system, you have to use the large enclosure for that. For the in-over system from Bruker, you can use the standard air table with it and then just put on the in-over cover again to reduce acoustic noise, because this is one of the major problems then if you have acoustic noise in there, or if you have just an airflow which you wouldn't really realize when you are working at larger scan sizes. You have to use a fresh sample for the mica. So basically, since this is a layered crystal, it's pretty easy. You can peel off the top layer, and you should do that right before the experiment so that it stays fresh and clean. Again, this is also crucial. And you can use Scotch tape to stick on the top surface and then peel it off quickly. You should have a look at the layer you removed. It should be a complete layer. You can see it here where it says perfect, so it should be a complete layer which is removed, not only a partial layer, because then you still have some dirt on your surface and might run into problems if you're scanning in this area. Sometimes it helps to peel it off a couple of times. However, what happens then, and these are two things actually, is then when you peel it off with a Scotch tape, it might lead to electrostatic charging of the surface. And this would basically also then not allow your system to work properly. For instance, especially since if you have silicon nitride layers, as it is the case for the SNL-C type, they can have a static charge themselves, and then you have a really bad engage or no engage at all for the multi-mode system. And this is actually a large, long-range interaction, so this might just bend your tip away from the surface or attracts very fast towards the surface, but you cannot then lift off from the surface if you're on the surface, which then means that you cannot really have a nice, good scanning conditions. And for that, we recommend an anti-static gun to remove the charge from the probe. After that, when you then have your standard scanning conditions to engage, you should increase the deflection set point to be sure that you're really scanning on the surface, that it's not, again, either surfing on something like a very thin water layer or on a charge, more or less. When you see the surface, then you should reduce the set point that you just lose the tracking. You can see that on the right-hand side. And then you slightly increase it that you just start again scanning on the surface. And by the way, this vertical deflection still might drift while you're scanning again. So this are in very small Z heights. So this means that maybe also you can have a very small drift in Z, and therefore you might have to readjust slightly your vertical deflection. And if you're happy with the scan conditions, and if you know that you're sure that on your surface, the best thing then is actually to apply an XY offset, that you're still in contact with the surface, but you go to an area where you didn't work so much on the surface, meaning either moving parts away. So this would be then better if you go to a fresh area while you're engaged on the surface. And as I mentioned before, the friction signal gives a better contrast. So at a high scanning rate, you have a problem more or less to track the atomic features with the feedback on. Therefore, it's better to keep the force constant, and therefore you would reduce the feedback gain that you have a constant force. And again, you have to scan 90 degrees because that allows you to get the friction channel in the contact mode experiment. And you can see here on the image from trace and retrace that they are both giving you a nice resolution with different, again, interaction, but you can still see the atoms there. Now I'm coming to the rounding, which is an artifact which shows up when you scan at very high speeds. You won't see that on the standards 1 Hertz or something like that, but you see it if you scan faster. That basically at the turnaround of at the end of the scan line, you will create an artifact where it's either, depending which channel you're looking at, it's either on this side you can see it's like a black line or trench which goes down. If you choose the other friction channel, it might be just a white trench, white line going up. This comes again from the sudden return of the scan direction. Again, it's an artifact. To get rid of that, there's a value which is called rounding, which you can change. And you can see that in the Calibrate Scanner menu, where you can change the rounding minimum value. However, you can change the rounding also while you are scanning in your scan parameters. And this would allow you a larger, so the system itself scans a larger range. Like the rounding of 0.2 means it scans a range of 1.2 times the scan size you see, but then has again, so it's like 20%. The scan is larger, so it returns then within this 20%, and so you don't see the rounding effect any longer on your image, or you still keep the same scan size. So it is, again, therefore removing this artifact from the image. You can see it again. And now I'm coming to the drift control, where you basically can see if the system is drifting. You might see some atomic distances, but you don't get atomic single atoms to be seen because the system is just still floating around. One of the ideas we have, and which is nicely working, at least if you prepare your samples fresh, meaning also gluing your mica, for instance, on your steel plate, you shouldn't use double-sided tape for that, because double-sided tape takes a long time to settle, more or less. So we would recommend epoxy glue or something like that to glue your crystalline layer on the substrates. The next thing to reduce the drift would be then to scan faster. You can see it in the image. You see on the left-hand side 10 Hertz scanning, on the right-hand side in the friction channel 60 Hertz, so you can see a much clearer image when you're scanning faster. And you should warm up and stabilize the system to reduce the drift, meaning so it should take a bit time. So you should turn on your system and should wait when everything is loaded, something like 15 minutes that everything is warmed up. Then always what's the question is it an atomic feature you're seeing, or is it just noise? So one of the tests is if you increase the scan size, you should see more features in the image, but the noise should be still the same if you just double the scan size, for instance. If you increase the scan speed, you should have still the same amount of features, but your noise pattern will change. And this is most probably the strongest hint on that. So if you just increase the speed again, you would see the noise. You would see that the noise, if it's noise, you see then the distance of the noise changes towards each other. This was about right now for the multimode, because again, this is a system that allows you pretty nicely to see atoms and atomic layers. If you would work on an icon system, you would have to turn off the closed loop, because the closed loop sensors in the icon scanner would basically cause so much noise that you cannot see your atoms. Same goes for the ANOVA system from Bruker, where you have to select the small scan contact mode in the experiment selector, where the system is then using the settings for the scanner, but without using the sensors. So the height sensors and XY closed loop sensor signals are turned off for the small scale scan. And then you should also be able to see your atoms in contact mode, for instance, on the ANOVA system. So the procedures, again, for the atomic resolution would be set up the tip and sample distance and align the laser. In the case of mica, peel off the top layer, mount the sample on the AFM, put a fresh probe in the holder, discharge the static charge on the cantilever and on the sample, mount the probe holder, align the laser and the photodiode, put on the acoustic enclosure, and then you set up your engage and scanning parameters properly, so that you're already in a range like 10 nanometers or 20 nanometers for the scan size, for instance, and reduce already your gains. And then you can engage on the surface. As soon as you're on the surface, you decrease the deflection set point slowly until the tip retracts from the surface, and then you would increase the set point again to let the tip just engage on the sample and to have a minimum of loading force that you are not wearing off your tip or your surface. Then you adjust the scan speed, scan size, and scan angle to optimize your image. Again, in the case of contact mode, scan angle means to be optimized will be 90 degrees for the friction. And then you might still need to adjust your deflection set point after a while during scanning, because there might be a slight change in there. So there's some questions my colleague put in here, like how to reduce the thermal drift in the image. Again, let the system warm up. Do not use double-sided tape, and scan fast. If the vertical deflection keeps changing during the tip engage, what is the problem and what is causing that, and how to fix it? So again, this is the electrostatic charging of either tip and or surface. So you need an anti-static gun to overcome that. Why would we use a low feedback gain? Again, to keep the force constant, then you can more easily see the atoms. And what data channel has the best image contrast in contact mode? Again, this is the friction mode. And what kind of probe is preferred? Actually, again, a soft and short probe like the SNLC, which has a very low spring constant and is also not very long. Well, I'm coming to that now, or actually now before that, it's the HOPG with an STM mode, again available for the easily available and easily achieved on the multi-mode, I have to say. So here the image was made with an A scanner, but you can also get atomic resolution with a STM with an E scanner. As a probe, we would suggest the platinum-iridium probe. The advantage towards, so you have, this is a conductive wire which is really sharp by either manual cutting or by etching, depending if you do it yourself or if you buy them. And the advantage of platinum-iridium versus usually the other option would be tungsten is that platinum-iridium is less oxidizable than tungsten. So if you cut a fresh tungsten tip for measuring in air, you can basically measure with it within 1 or 2 hours, and then it starts to oxidize. Then you would have to cut it again. Therefore, platinum iridium is more or less the probe of choice. The scan size in this case is 5 nanometers. The scan rate is 40 Hertz. The gains are set to 0.1 each. The bias for the H2PG, again, it has to be for STM mode, it has to be a fully conductive sample and a conductive tip, otherwise STM will not work. The bias is here around 50 millivolts. Personally, I can say it would also work with up from, let's say, from 10 millivolts upwards to 200, again, depending on your conditions of the tip in the system. The current set point is here, in this case, 2 nanoamperes. It could be also 1 nanoampere. I did my measurements a long time ago with 1 nanoampere. It also worked nicely. Again, turn on the rounding, in this case 0.2. The resolution here is 256 times 256, and the data channel here is the current, because again, like in the AFM contact mode, the current can be compared to the friction, because you see the systems run more or less at a constant height, and you see then the current flowing in and out of the tip. And the height channel will be more or less of no information. On calcite, as a third example, you can see here with peak force tapping. In this case, this was done with a multimode and an E-scanner. It was a fast scan C probe, 50 nanometer scan size. Scan rate was 4 Hertz in this case. The peak force amplitude was reduced to 20 nanometers. The engaged set point also pretty low at 0.04 volts, while the set point itself for the measurement is at 0.02. So we have a very soft engage so that we are not damaging the tip while engaging, and then we increase it a bit to get better tracking. The feedback gain was set to 2. The rounding in this case, since we are not scanning very fast, was set to 0. And we have a 256 times 256 resolution here, and the data channel is height. So here you can see that the rounding, again, plays a big role when you scan faster. You don't have the rounding effect when you scan, in this case, at 4 Hertz. So this is a bit about the AFM cantilever and the optical lever, meaning how sensitive the or the sensitivity of the cantilever is characterized by the deflection sensitivity, and the units is in nanometers per volt. And a short cantilever has a better deflection sensitivity because it's proportional to 1 divided by the length of the cantilever. So this means in the end, short and soft cantilevers are the best for atomic resolution. One more thing is, again, if you have a dirty fluid cell, then this will deteriorate your deflection sensitivity. And the same cantilever on different AFMs will have different deflection sensitivities. Just keep that in mind. If you come from a multimode and go to an icon or vice versa, the deflection sensitivity for exactly the same cantilever will be different, because mainly the laser path is different, meaning longer or shorter. So which are the probes for the atomic resolution? Again, this would be here where you can see the SNL probe, for instance, where you have the A, B, C, and D cantilevers, and as before, small and soft in this case for the cantilever is the best choice. So it has the better deflection sensitivity because they deflect more, and you have a better force control, so they are not so stiff. You're not destroying the surface so easy. And in addition, it has a less hydrodynamic damping when it's operated in fluid. The recommended probes, again, are the SNL-C probe. So here at the bottom, the thin cantilever, but the short one, which has a length of about 120 microns. The scan is Fluid Plus, because it's sharper, so the tip itself is sharp at 1 or 2 nanometers radius, and has a length of 70 micrometers, and the fast scan C, also 2 nanometers diameter, has a length of 40 micrometers. So these are the ones we are recommending for atomic resolution. To control the contamination, and this is a very important thing. If you work in liquids, for instance, you have to clean technically everything you're working with. You should wear gloves all the time, and you should start out with cleaning your tweezers you're using. You also should wash the fluid cell and the sample with a soft toothbrush. Here it says baby brush. Here's a small difference to the presentation here. I personally recommend not using soap water, because then you would have surfactants which might not be rinsed off by water. But nevertheless, so you could try something like, again, IPA, or just water, clean DI water, and then rinse a lot. And then you would dry the cell with clean nitrogen or compressed air. If it's clean, you have to be sure that your compressed air coming from the wall outlet is clean. You shouldn't use these cans with compressed air, because they usually contain also oil, and then you would have, again, surfactants and oil on your cell, and this would contaminate your measurement. And if you transport your cell around from the area where you did the cleaning, you should put it in a container that it's not collecting dust while you're carrying it around. Again, you should wear gloves when you handle it. Okay, there's one thing: you shouldn't breathe on the sample or the probe holders. So if you think there's some dust on there, use the dry nitrogen or the compressed air, but not your breathing. Use, here it's called analytical grade pure water, like the MilQ millipure water available, because the standard deionized water is not clean enough. Usually you have still something in there. The MilQ millipure water is then using also UV light to kill any organic substances inside, and it's still filtering. And you should use a clean, fresh pipette or syringe to add water to the tip and to the sample. And here you see an image like standard DI water versus the analytical grade water. And you can see on the left-hand side huge contaminations, and on the right-hand side there are just a few or even almost nothing. And again, you would need the pure water for the atomic resolution in fluid. The regular water, even if you filter it afterwards before you put it in, is not clean enough. And the problem is more or less that the soft particles from the DI water will, in this case, deposit on the calcite, and usually they stick to the edges because they're the most reactive. And then what might happen during the scanning is basically that these particles will stick to the tip afterwards and not stay on the calcite. And then you have a contaminated tip where you cannot get any atomic resolution with. For the setup for the multi-mode in this case, what I usually prefer is you would do your first approach to the surface in air without the water, if possible. In this case, if you're looking at calcite, it is possible. So you would align your laser in air, engage on the surface, withdraw once, because then you know that the multi-mode then is about 20 microns away from the surface. And then you could put a droplet of water on the calcite and a droplet of water on your cantilever by turning the optical head around. Then you should put everything together. In this case, or if you want to keep your calcite more clean or get it more clean, you can basically put on a droplet of water, wait for 5 minutes that the surface active features are dissolved, then remove the water again and repeat this a couple of times. Then you would have a very clean calcite surface. And for the peak force engage on that, you again would minimize your set point to 0.04 volts and reduce your amplitude to 20 nanometers. I think the default is around 100 or 150. You have to turn off the auto control for the scan assist, that you have your feedback gain set to 2 and your set point for the measurement to 0.02 volts. Again, the peak force amplitude should be the same as for the engage amplitude, and the frequency 2 kilohertz is fine. And you should check if you can even further reduce the set point without causing a false engage. So touch the surface as soft as possible. When you're on the surface, you use the auto config button in the force monitor to adjust your sync distance new to make sure that you have a good feedback on the peak force. If it's not easy to do that with the auto config, that it's not stable enough, then you would have to do it manually, and you type in a value then for the sync distance new and see until the blue and the red curve where you have the hard wall contact of the force curve, where you have the approach and retract are on top of each other. Then you know that you have a good sync distance, and then you can start with your experiment. Again, you can still then further adjust your set point again to minimize, and your amplitude to have a very, very small amplitude to give you a better resolution for your measurement. You should constantly monitor the scanning and use an offset to avoid scanning over contamination. So if you have contaminations, zoom away from them or use the offset to get away from them. And then you can look for different scan sizes to find a good location for scanning. And for instance, edge is pretty nice for that. And you can then zoom in on that. The recommendation or recommended scan speed is 4 Hertz if you're scanning at 256 times 256 data points, or 2 Hertz if you're at 512 times 512. You can see here that you need a bit less speed for that, as in contact or in STM mode. Again, you might still have some drift, therefore here you might have to wait a bit longer that the drift settles out and that you don't have a problem with the drift any longer. So again, be patient. So here's again the summary of the procedure for the atomic resolution in tapping mode. You have to set up the tip sample distance and the laser position in air, makes your life easier. You clean the sample and fluid at a sink with deionized water or molecular water, depends on you. Meanwhile, leave the system to warm up and stabilize. Further clean the sample with pure water and leave a small drop of water on the sample surface. You shouldn't spill the water on the sample, so just a small drop. Sorry, don't overspill, so you shouldn't rinse it more or less in water. You mount a fresh probe to the fluid cell holder. Add a drop of pure water to the wet the probe itself. Because if you do not do that and you have a triangular tip, for instance, a V-shaped tip, you might get air bubbles or an air lamella actually, which is then causing problems while scanning. So it's always better to put a small drop of water on your cantilever. Then you mount the sample, install the fluid cell, and align the laser and then the photodiode as quickly as possible. So for a multimode, you have to remember that you also have to adjust the mirror of the optical head, because the laser path changed due to the water. Recommended is to wait about 30 minutes to stabilize, to minimize the drift. And most probably then also you have to readjust your photodiode again. Then you set up your engagement scanning parameters as before said, so very low forces, small amplitude, and then you start to engage. When you're on the surface, you start to optimize the scanning parameters, adjust the X, Y offsets and the scan size to find a good location for the scanning. So coming to the question part here again, so how to control the contamination. So first of all, work clean, use pure analytical grade water if you work in water. How to control the drift with the peak force tapping is basically you have to wait longer for the system to stabilize. How to keep the tip sharp again is to avoid running into contaminations, which should then and to minimize the forces. And what kind of probe is here preferred? Again, a short and soft cantilever. As mentioned before, the SNLC or the ScanAssist Fluid Plus actually would be the best choice here, or the Fast Scan C. That's it from my side. I hope you have some questions. Let me see if I can find my way through the, here we are. There's the dashboard. This is pretty new to me. Here's the chatting. Okay. So, okay, some questions from your side? Hello?
So I see that we have two questions for now. First one is, does SIN cantilever have positive charge or negative charge?
Oh, it's a good question, which I cannot answer. It wouldn't play a role in the liquid, though. And with the anti-static gun, it doesn't matter, because I know, if I remember correctly, if you press the anti-static gun, either you press it or you release it, and you would create both kinds of charges to reduce the electrostatic charge.
Okay, and the second question, how to clean the probe? Does the new probe need to be cleaned?
A new probe doesn't need to be cleaned. It should be clean in general. So just to be sure that you always take them from a closed box. It doesn't have to be a fresh box, but that you open the container where you have the probes are stored in, that they're not lying around in open air. Then they should be clean enough. If you have a contamination on your probe, usually this is getting kind of tricky. From my experience, I can say that UV light would help. So if you would put them under, more or less put them under an ozone light, where you create an ozone underneath, and then you would again get rid of the contaminations. I know there are people who were using like a dried ice gun for that. I never personally went there. Again, try it with UV light or with carefully rinsing in clear water, see if it gets rid of the contamination. On the other hand, most of the times, look for a new probe. Actually, it's the easiest way.
Okay, thanks, Chris. And we have two other questions. One is from Ahmed. He asked, is there any way to decontaminate the tip, for example, ScanAssist fluid?
Again, so there are some ways. Again, you have to look into the literature. From my personal experience, in and out of the lab, ozone will help. So if you have something like a UV light, which would create ozone, you could get rid of the contaminations. And this is actually also what the millipore system is doing, or the milliQ system is doing. It's using UV light to reduce or kill the agglomerates in the water. And this could be done. This would be one way. Again, no guarantee there. And I know that people were using dried ice guns, which I think is a bit aggressive, but might help you. But please look into the literature for that.
Great. So we have the last question from Isabel. She's asked, do you have other examples beside mica?
I think it's molybdenum disulfide, which is also nice, and it's also conductive, so you could use it for STM, and if I remember correctly, also for contact mode AFM. For the rest, you have to look for, how should I put it, layered crystals, because these are the easiest to clean and also to peel off, or to get a fresh and clean surface. But I know that molybdenum disulfide also works. The rest I would actually have to check my literature, but I can, if I have your email address, I think that should be, because you're registered, I can send you an email about that, of other atomically flat substrates.
And can you look at the biological specimens as well? That question from Isabel.
Yes, you can look at, for instance, DNA. You will not get molecular resolution, but you will see the double helix. That's possible. Again, so if you usually also attach your DNA, for instance, on mica, because it has to be rigid on the surface. And then you can look for that, and also you use a very sharp tip there. So it's possible, but you wouldn't see, let's say, single strands of DNA or single molecules of DNA. No, how's it called? No amino acids as a single molecule, but you could see still nicely the double helix.
Okay, so we'll wait for another few seconds to see if there are other questions. Oh, so as Isabel asked, will a 5-micron scanner work?
A 5-micron scanner will work. So this is, I think 5-micron is, oh, it is most probably then the Innova system. Isabel, is this correct?
Yes, that's correct.
Okay, yeah, this will work.
Okay, we'll see if anybody else has questions. Okay, great. Thank you, Isabel. And thank you, everyone, for coming for this webinar. And the last, before you go, could you please just do a little survey at this survey section? We have just 3 questions for you. It won't take a long time. So we are at the first question. What describes best your situation? Okay, and the second question is, do you think the presentation today is relative to your research? Great. And then last question is, would you like to participate in our future webinars like this? Okay, meanwhile, we have another question from Chen Long. We also have optical profiler, but I missed the last webinar. Is there any way to see the record? That I could answer. The answer is absolutely yes. So in next week, we're going to send everyone the recording as well as the presentation link, so you could see afterwards. Okay, great. So thank you again for joining our webinar, and I hope you really have your something learned. And if you have further questions, don't hesitate to contact us. And have a nice day.
Okay, thank you all for listening. Talk to you next time. Bye.
Bye-bye.